Next, we will introduce a special type of series called geometric series, and it is very important for anyone to be able to recognize it because geometric series have very nice properties. So let's get started, and in order for us to define a geometric series, we need to consider a geometric sequence. And geometric sequence has a general formula like this, in which B represents the first term and R represents what we call the common ratio. And when we have such setup, all we have to do is take the general formula, put it in big sigma notation, and this construction will be called a geometric series. So geometric series represents the sum of all the terms of a geometric sequence. And of course, the main question that we have to answer is this: does this series converge or diverge? And we already know that any series, including this one, will converge when the sequence of the partial sums converges. So if we know the formula for the sequence of partial sums, then we can tell whether this series converges or not. So the goal is to figure out the formula for the sequence of partial sums. So now, what would be the nth partial sum? It will be the sum of the first n terms of the sequence, well, n series, and here's what it looks like. You may ask again, why is it n minus 1 when we're considering the sum of the first n terms? And the reason is because we're starting with the power of r being equal to 0. So from 0 to n minus 1 will give us exactly n terms. And now we can simplify this by factoring out b. And if we factor out b, you're going to have this left. And here we're going to do a little trick. I want you to recall the following formulas from algebra. 1 plus x times 1 minus x was equal to 1 minus x squared. 1 plus x squared multiplied by 1 minus x would be equal to 1 minus x cubed. And I'll let you guess, what do you think this is equal to when multiplied by 1 minus x? The correct answer is 1 minus x to the power 4. Now, being inspired by these formulas, we're going to multiply this expression by 1 minus r and divide it by 1 minus r. And we're going to simplify the numerator using those formulas, and the numerator just becomes 1 minus r to the power n, and the denominator remains the same. So the question is, now, since we now have the explicit formula for the partial sum sequence, the question now is, what is the limit of the partial sum? And if we plug in this result into the limit, it becomes pretty clear that the limit depends on the on what's going on with r to the power n. And we know that raising numbers to large powers produces different result depending on the number that you raise to the power. If you take a small number whose absolute value is less than 1 and raise it to the power n, the r to the power n will go to 0. And in such a case, we're going to have left b over 1 minus r. However, when you take the large powers of large base and raise it to the infinite power, then that will become a very large number, and regardless whether it's a positive or negative infinity, it's just going to be a large number, and then in that case the limit does not exist. So this is the result. So basically it says if r, the common ratio, is less than 1 in absolute value, then the limit of a partial sum exists and it's equal to this expression. Otherwise, it doesn't exist. And we summarize this by stating the following fact. The geometric series converges to b over 1 minus r when the common ratio, the absolute value of the common ratio is less than 1, and it diverges when the absolute value of r is greater than or equal to 1. So let's do a couple examples. Let's investigate the convergence of this series, and the first step is to recognize this as a geometric series, and we can do that by rewriting the series in this form. So now we identify the initial term and the common ratio, and once we do, all we have to do is to confirm that the common ratio, which is 1/3, is less than 1, to conclude that the geometric series converges to the following expression, which is equal to 3. Now, the hardest step in this whole process is to actually recognize that you have a geometric sequence, and that's why knowing how to work with geometric sequences, this is why it's becoming important. And luckily we have practiced that in one of the previous lessons. So when we see a series that's written like that, we have no problem actually breaking it down into the standard form by pulling out 2 from 6 and then combining the 3's and rewriting it like this. So again, this is of course the same exact series as the one above. The point here is that not always the series will be given to you in a way that we call the general form of a geometric series. So not always this power will be n-1. So you have to know how to identify the geometric series, and there are multiple ways of doing it. And let's consider the following example. Now, how do we know that this is a geometric sequence? Because this is the main concern here. Is this geometric? One way is to try to write a few terms of the series. So when k equals 1, we have 2. When k equals 2, we have 1/2. When k equals 3, we have, what is it, 1/8. How am I producing these terms? I'm just plugging in k1 here, k equals 2 here, k equals 3 here, and so on. So if you can do that, so if you suspect some sequence to be geometric and you can plug in a few values, then the first term that you'll see clearly is your b. Now take the second term, which is 1/2, and divide by the first term to produce the common ratio. The ratio will be the same regardless of which two consecutive terms you take. It's always going to be the same. That's actually one of the properties of geometric sequences. So this is one way to identify that we have the following geometric series. And if that's the case, then the sum will be equal to the first term divided by 1 minus the common ratio, so it will be 8/3. Now, this was one way of figuring out that you have a geometric sequence or series. Alternatively, we can do it by manipulating algebraically this expression. So instead of having 4/2⁴ minus 1, we can start simplifying things. So we can write, instead of 4, 2 squared. Instead of 2⁴, I guess it didn't help us to write it as 2 squared, so let's just keep it as 4. And instead of 2⁴ minus 1, we can write it as 2⁴ divided by 2. And then instead of 2⁴, first of all, we can also bring this to the numerator. And then instead of 2⁴, we can write it as 4⁴. But remember, we don't want to have it as a 4⁴. We want to have it as 4⁴ minus 1. So we can do that, but that will basically remove 4 from the numerator. So you see how we were able to manipulate this expression algebraically and rewrite it like this, which is exactly the form of a geometric sequence. So from here we learned that this is b and this is the common ratio. So one way or another we are going to know. Now let's practice this process again. So let's take now the series, but this time we actually want to start at 0. And it doesn't even look like a geometric series here, but if it is, then all we need to know is b and r. Now, we can try to just plug in some values, like for example, when n is 0, what are the terms? We're going to have 3. When n is 1, we're going to have 8/3. When n is 2, we're going to have 2 to the 6 is 64/2, so 3 to the -3, so it's over 27, and so on. So what do we see here? Well, the first term is b, and the common ratio can be found by taking the second term and dividing it by the first term, so it's 8 nines. So before I plug it in into the formula, let's try to manipulate this algebraically. So let's take 2 to the power 3n times 3 to the power 1 minus 2n, and let's rewrite it algebraically. So this time, since we have the index starting at 0, which is unusual, we're going to actually keep track of the entire series here. Now, the first thing we want to do is we want to reindex our series. And what does that mean? That means if I want my series to start at 1 here, I have to subtract 1 from every appearance of n in the formula. So that's the first step. Now we're going to simplify this, and as we're simplifying, we plan how to turn this into the desired format. And 2 to the power 3n minus 3 is 8 to the power n over 8, and 3 times to the power 3 minus 2n, it's actually 3 to the power 3 over 9 to the power n. So this is just like basic kind of algebra here. And we continue. So we have 27 over 8 nines to the power n. But remember, we need this to be n minus 1. And we can easily make that n minus 1 by multiplying everything by 8 nines. And things kind of work out nicely here, right? So we end up with the sum, n goes from 1 to infinity, 3 times 8 nines n minus 1. So we of course observed exactly the same first term and exactly the same common ratio. So regardless of which way you convince yourself that this is a geometric series with the first term 3 and the common ratio 8 nines, the end result will be the same. The sum is 27. Let's do another example. And let's plug in some values. So the first term here, we're noticing it starts at 3. So the first value I'm going to be plugging in is 3. So it's going to be 4 cubed times 2 to the power 0. So it's 64. Now A4 will be 4 to the power 4 times 2 to the power negative 1. So that's 256 by 2, 128. And what do I see here? So this will be my first term, and my common ratio will be 128 over 64, which is 2. Since 2 is greater than 1, then the conclusion is that this series diverges. Here's another example. If we have a series that's not given to us by a formula but written out explicitly like this, for example, then the first thing we need to do is immediately we can identify the first term, b, and we can immediately identify the common ratio. So the common ratio here is -6/5 over 3, so which is -2/5. Since the absolute value of the common ratio is less than 1, we conclude that this series converges to this expression. And regardless of whether your common ratio is positive or negative, the formula works. So the final answer is, in this case, 15 over 7. Before we finish this conversation about the geometric series, I want to say a few words about arithmetic series. And if we wanted it to define an arithmetic series, we would consider first the arithmetic sequence. And arithmetic sequences, they all have the same general formula. And we would define the following expression as the arithmetic series to be but what makes arithmetic series so boring is the fact that they always diverge. Basically, there is nothing interesting going on with arithmetic series. Regardless of what A and D are, the sum of infinitely many numbers that none of them is approaching to 0 will be equal to infinity. For that reason, we are absolutely not interested in studying the arithmetic series, but only interested in studying the geometric series. And this concludes the lesson about the geometric series. Hopefully you learned how to identify one and how to determine whether it converges or diverges based on the common ratio.